From the high-resolution images of an MRI scan to the massive particle accelerators at CERN, the ability to calculate and control magnetic fields along the axis of circular loops is fundamental to modern physics. Today, we will derive the formula for the magnetic field at any point on the axis of a current-carrying loop and understand its physical implications. In many engineering applications, we focus on the central axis because the symmetry of the loop simplifies the magnetic field vectors. Understanding this specific case allows us to build complex devices like Helmholtz coils, which are used to cancel out the Earth's magnetic field or create highly uniform environments for scientific experiments. Before we dive into the math, remember the fundamental rule of electromagnetism, the right-hand rule. When current flows through a wire, it generates a magnetic field that circles around it. In a circular loop, these individual field lines combine to create a concentrated field passing through the center of the ring. Let's set up our coordinate system. We place a circular loop of radius r in the YZ plane so that its center is at the origin. We want to find the magnetic field at a point P located on the x-axis, at a distance x from the center of the loop. Consider a small element dl at the top of the loop. The distance from this element to our point P is the hypotenuse of a right triangle formed by the radius r and the axial distance x. Using the Pythagorean theorem, the distance r equals the square root of r squared plus x squared. According to the Biot-Savart Law, the direction of the magnetic field dB is perpendicular to both the current element and the radius vector. This means dB's at points PE points at an angle. We can split this vector into two components, one along the axis and one perpendicular to it. Here is the beauty of symmetry. For every current element on one side of the loop, there is an identical element on the opposite side. Their perpendicular components are equal in magnitude but opposite in direction, so they cancel each other out completely. Only the components along the axis add up. Since only the axial components matter, we integrate dB times sine of theta around the entire loop. Note that sine of theta can be expressed as the radius r divided by the distance r. This allows us to rewrite our integral in terms of constants and the length of the wire. The integration is straightforward because the distance r is constant for all points on the loop. The integral of dl is simply the circumference of the loop, 2 pi r. After simplifying the constants, we arrive at our final expression for the magnetic field at any point x along the axis. Let's look at a specific case. When x equals 0, we are at the very center of the loop. The formula simplifies significantly to mu0 times I, divided by 2r. This is the point where the magnetic field is at its maximum strength because all parts of the loop are at the minimum possible distance from the point. Suppose we have a loop with a radius of 10 centimeters carrying a current of 5 amperes. By plugging these values into our center field formula, we find the magnetic field is approximately 31.4 microteslas. This is roughly comparable to the strength of the Earth's magnetic field. When the distance x is much larger than the radius r, the r squared term in the denominator becomes negligible. In this region, the magnetic field decreases with the cube of the distance. This is characteristic of a magnetic dipole, similar to how a small bar magnet behaves at a distance. We can express the far field strength using the magnetic dipole moment, m, which is the current times the area of the loop. This highlights a deep connection in physics. A tiny current loop is the fundamental source of magnetism, behaving exactly like a microscopic north and south pole. If we move to a point 50 centimeters away from a 5 centimeter loop, the approximation becomes very accurate. Calculating the field here shows how rapidly the strength drops off. This is why you must be very close to an electromagnet to feel its pull. If we plot the magnetic field strength against the distance x, we see a symmetric bell-shaped curve. The field is strongest at the origin and tapers off in both directions. The width of this curve is determined by the radius of the loop. A larger loop creates a broader, flatter field. What if we have more than one loop? If we stack n turns of wire closely together, the magnetic fields add up linearly. This is the principle behind a solenoid. By understanding one loop, we can calculate the field for a long coil used in everything from car starters to electronic locks. A special configuration called Helmholtz coils uses two identical loops separated by a distance equal to their radius. In the region between them, the decrease in one field is perfectly compensated by the increase in the other, creating a remarkably uniform magnetic field. This is vital for precision physics experiments. It is important to note that our simple formula only works on the central axis. Once you move off axis, the symmetry is broken. The math becomes much more complex, requiring advanced calculus and elliptic integrals to solve. This is why engineers prefer to place sensors on the axis whenever possible. A very common mistake is forgetting to convert units. Magnetic constants are defined in Tesla, amperes, and meters. If your radius is given in centimeters or millimeters, you must convert it to meters before plugging it into the formula, or your result will be off by orders of magnitude. Don't forget that magnetic field is a vector. If the current direction is reversed, the magnetic field direction on the axis also reverses. Always use your right hand to verify if the field is pointing into or out of the loop relative to your point of interest. The denominator in our formula is raised to the power of 3/2. This comes from the combination of the Law squared from the Biot-Savart Law and the sine of theta geometry. Using a squared term instead is a frequent error in exams, so double-check your exponents. To summarize, the magnetic field on the axis of a circular loop is highest at the center and drops off as you move away. The derivation relies on the Biot-Savart Law and the cancellation of non-axial components due to symmetry. This formula is the foundation for designing solenoids and electromagnets. Let's test your understanding. Look at the center field formula, B equals mu naught I over 2r. If you double the radius of the loop but keep the current the same, how does the magnetic field at the center change? Think about the relationship between B and R. The correct answer is B, the field is halved. Since the radius r is in the denominator, increasing the radius pushes the current farther away from the center, weakening the field. Thank you for watching this deep dive into electromagnetics. Generated by Vision Solve AI.